So now suppose that we have a tensor product state, say 1, which is of this form, psi1 A cross phi1 B. Okay, such states are called product states.
So why was this index used, one index?
Because I'm soon going to introduce another product state called psi2.
Oh, अच्छा.
Okay, chi2. Sorry, not BB. Want AB here, AB here, okay? And suppose I have another product state, a different state in principle. Now these are both elements of a vector space HAB, right? So we are allowed to take their linear combination, and according to quantum mechanics, their linear combination is also a physical state. So suppose I take the linear combination and call it chi of AB is some constant C1 chi1 of AB plus C2 chi2 of AB, right? Now, if, for some choice of C1 and C2, there does not exist a basis such that we can write it as a such that we can express chi AB as a product state, then we say chi of AB is an entangled state. Okay. Again, this is not a very mathematically rigorous definition, but you know what I mean is that because for non-zero values of C1 and C2, this is not going to be written as products, right? In general. And if you can't do that, then this will be an entangled state. Okay? So for example...
So could you repeat this point?
Yeah, let me give you an example. For example, we look at the product state of an electron and a proton. So this is a product state because, we can write it in terms of, two states which clearly belong to two different systems. And there's a tensor product. But if I add to it, say, minus the spin down state of the electron and the spin down state of the proton, then I can normalize it. Say there's a square root of 2 and there's a square root of 2. There can be an I here, I don't care. But this cannot be written in a form where there, which is a state of the electron, say, let's call it, this cannot be written in any basis in this form. And therefore, this is an example of an entangled state. So, but if you had chosen this to be like that, and the second one to be minus E and then plus of P, then of course, these guys are common to both. So you can rewrite this as square root of 2 plus E plus 1, I by square root of 2 minus E times plus P, which is of this form. So this is not entangled. Okay. So, I don't want to go deep into entanglement today because this is not the point of our lecture. But I just thought that, I just think that whenever the idea of tensor product arises, entanglement comes in naturally. And therefore, I wanted to point it out, okay? Now, does that make it more clear, the example?
Yes, sir.
Okay. Any questions?
I'm still not quite sure about what it means
So
to
in this,
Oh, sorry. Go on.
yeah, I wanted to ask, like, in this case, could you like define what you mean by entangled state?
Yeah, because this state cannot be written in this way. That is entanglement. It cannot be written as a product of a state in electron and a state in proton. It is a sum of two states, two substates, but it is not a simple product. Okay? Whereas this thing is also a sum of two states in the Hilbert space, but it can be rewritten because this guy is the same here. It can be rewritten as a product of a state in the electron Hilbert space and a state in the proton Hilbert space, and therefore it is not entangled. Okay? Wajiha, does that make it clear?
So if we can write the states in different forms, then it's not entangled, like separately.
If you can find a basis in which the state can be written as a product like this, then it is not entangled.
Oh, okay. Yeah.
So entanglement is defined in a kind of a negative way. And as you know, entanglement is a powerful tool in quantum computing. And entanglement contains in it some of the spooky sort of action at a distance, which cannot be simulated by classical physics, and which is the subject of Bell's theorem. And so a lot of these, automaton, models of reality that are proposed by various people, including what's his name, the Mathematica guy, doesn't really work because they can't simulate the result of entanglement. Anyway, that's a separate issue. Okay, let me then move on. And by one more comment, which I'm not going to explain, but you will see in action, is that operators, acting on the two different Hilbert space, HA and HB, commute.